Now, let's move on to the next topic, that is buckling analysis of this particular module. So, what is buckling, anyways? But before that, we must know what is column. See, to understand column, see, it is a vertical member. It is a vertical member where compression load will be acting. See, this is a vertical member. Okay, see, it is a vertical member. Column is a vertical member in which compression axial load will act. Now, compression axial load, I am saying axial load means the load P will pass through the axis of the column. But if the load has some eccentricity from the axis, something like this, check out here. This is the axis of the column, and let's say the load is here. We have some sort of eccentricity or distance from the center. So E is the eccentricity. So just tell me whether it is a column or not. Obviously, this is also a column because it is a vertical member and also the compression load is there. So that's the main criteria for column. Okay, exactly. Now, what is buckling analysis? Let me explain. You can understand this whenever a column is loaded with a compression load and the column starts bending. Like, see, this is the column, and let's say this column starts bending due to the compression load. The column starts bending. See, this is the bending. That bending is known as buckling. So that will be known as buckling. Okay, this is the buckling. The column will try to buckle. Now, one thing is for sure, the column must be long enough. Then only the buckle will happen after applying the load. Okay, the column must be a long column. For long columns only the buckling will occur. Okay, so it's a kind of bending. And remember one thing, buckling is a analysis for a column where you can say it's a type of failure where we can call it as an elastic failure. Buckling is an elastic failure. No, what does that means, elastic failure? Actually, see, suppose you have a house. In your house there is a column. Suppose that column starts buckling, then your house will start vibrating, right? And that thing we don't want. So even though, suppose if I remove the load, see, it has started buckling. This column has started buckling. Now if I remove the load, then the column will again regain its original shape, because what I am saying, it is an elastic failure. What I am saying, it is an elastic failure. Once the extra load which came to the house where the column starts buckling, okay, that extra load is removed, then again the column will come to its original shape and size. So that's the elastic, right? Because of the elasticity. So that's why buckling is an elastic failure. We don't have to go up to the plastic failure or fracture. No, it's an elastic failure. Okay, once you remove the load, again it will come to its original shape and size. But we don't want this buckling. We don't want this bending actually in our daily life structures where we use these long columns. Okay, yes. So See what they have written. It is the only area of structural mechanics in which failure is not related to the strength of the material. We are not bothered about the strength of the material. Strength of the material means yield strength, ultimate strength. We are not bothered about it. We only take care that it should not bend. Even if it is bending due to the extra load which come to the column and it starts buckling, that is not acceptable. The column must not bend, or you can say must not buckle. Even if it start buckling slightly also, that is not acceptable. Okay, so that's the very important part which I wanted to convey. So obviously, due to bending, suppose this column has start buckling, so some sort of bending stress will occur here. Some sort of bending stress will occur. If bending stress occurs onto these columns, that bending stress plus the axial stress which is coming, that combined total stress, that total normal stress must not exceed, must not exceed yield stress. What did I say? Obviously, once this column will start buckling na, the total normal stress onto this column should be less than or equals to yield. Obviously, this has to be taken care. We will take care of this. Yes, we will take care of this. This should not exceed. Okay, how to do those calculations we will see later. Now, the column buckling analysis consists of determining the maximum load a column can support before it collapses. See, once it starts buckling, means it is collapsing, and obviously we will not wait for the plastic deformation of the column or fracture of the column to occur. Even if it is in the elastic range only, even after this buckling, we don't want that. Even the elastic bending is not acceptable, elastic buckling is not acceptable, because our structure will start vibrating due to that. Okay, so we have to determine that maximum load to avoid buckling. That is the focus of this particular module. For long columns, the collapse has nothing to do with the material yield. That's what I am saying. Even though the stress, the maximum stress in this particular column will not reach the yield point or yield limit, okay, then also we will say that it may fail. Okay, because we are not bothered about the material yield. Okay, because yield is very far from it, because just even if it slightly buckle, it is considered to be fail. Okay, yes, it is instead governed by columns stiffness, both material and geometric. We will derive one equation, actually one formula for it, where we will see that the load which we are giving, that maximum load which we can give into this column, okay, into this column, that must be governed by material and geometry both. Okay, see, before that, whatever analysis we were doing, we were comparing the maximum stress with the yield stress or the ultimate stress. But here we will not compare our maximum stress with the yield stress. Actually, we will be quite lower than only, we will be quite lower than the yield stress, because here the load which is being act onto this will depend not only on the material, but also it will dependent upon the geometry. Geometry means its cross section, its length, everything. Yes, so that will define the column's stiffness. Objects are referred to as columns when they loaded axially in compression. That is already discussed. Okay, so the main point is that buckling is a elastic failure. Okay, buckling is a elastic failure. Yes, buckling is an elastic failure. That's the main point. Okay, elastic, elastic region. Suppose even the load is acting onto this particular column, and even the maximum stress which is being act here is inside the elastic region. Okay, suppose it is inside the elastic region, then also we will consider this column as a fail if it starts buckling. However, if we remove that load, then again it will come to its original shape and size, which is the opposite of buckling. It will come as straight, but it will affect our structure's stability, even if it is going to have um, slight buckle. So that's why we try to avoid this buckling, which is nothing but an elastic failure. Now we are going to study Euler buckling theory. First of all, we will be starting with the column with both side hinged. Okay, so let us start with this example. See, both side hinged. Here also hinged. Here also hinged. Both side hinged. It is hinged. Here also hinged. Both side hinged. So suppose, let us say I applied load P. Once I applied that load P, this column starts buckling. See, once I apply load P, this column starts buckling. And if this column starts buckling, see, it is going to bend something like this. So we have to find the minimum load P such that this column will start buckling, or you can say the column will start bending. Actually, it's a kind of bending only, right? So whenever the bending term is coming, then we have to take the advantage of bending things, bending equations and all those stuffs. Okay, so let's say after applying load P, which is the minimum load P, this column has just started buckling, and at this point C, it is the maximum deflection. Why is the maximum deflection with respect to this original position? So if I take a section here, let's say YY section, and if I can calculate bending moment about this C point, or you can say Y section bending moment, then what it will be? It is nothing but P into Y. Yes, already I have written here P into Y minus P into Y, because it's a kind of hogging. We are considering it as a hogging. So minus P into Y. And also we know this differential equation. See, already I have written M bending moment is equals to minus P into Y. And we know very well EI is nothing but the flexural rigidity. EI, suppose EI is the flexural rigidity. What are these things? E is nothing but Young's modulus, and I is area moment of inertia. What? Area moment of inertia. Exactly. Area moment of inertia. But E into I is nothing but flexural rigidity. Okay. Now, d2y by dx2, d2y by dx2 into EI is equals to M. This is the very well known differential equation in case of bending. Okay, exactly. Now d2y by dx2 into EI, in place of M I can write minus py. Okay, so EI d2y by dx2 plus py is equals to 0. So it is a differential equation. Okay, this is a differential equation. And obviously this differential equation will have a solution. Definitely it will have some solution. How to find out that solution? What is the solution to this differential equation? See, directly I have found out, because I am assuming that you know the differential equation very well. Once you solve this differential equation, you will have some solution. This is the solution to that differential equation, where a and b are the constant, and that will be determined with the help of boundary conditions. Now what are those boundary conditions? You can see here, from b to c point, let's say the distance is x. So at b, that is x is equals to 0, y is equals to 0. Obviously the deflection here at b will be 0, and at a point, this is the a point, right? The x is equals to L, because this is the total length L, right? Yes, this is the total length L. The total length of the column is L. So at x equals to L, y is equals to again 0. Okay, so we got two boundary conditions. Obviously we have two constants, so we need two boundary conditions. The first boundary condition is x is equals to 0 and y equals to 0. That leaves b is equals to 0. Put the value here. Put x and y equals to 0 here. You will get b is equals to 0. Once you put b is equals to 0 in this equation, then you will get this particular equation, which is nothing but y is equals to a sine under root p upon ei into x. And then second boundary condition. If I put the second boundary condition is what? For x equals to L, y equals to 0. So put the value, you will get this. Y equals to 0 is equals to a sine under root p upon EIL. Now, see from here, a cannot be equals to 0. That's why sine under root p upon EI into L has to be equal to 0. Remember, this L is outside the under root. This is equals to 0. Now, where does the 0 value exist in sine? Sine 0 degree, sine pi, sine 2 pi, all this are 0, 0, 0. So I can put sine 0 here, but that is not worthy. Then I will put sine pi here. So I put sine pi, then I can write pi is equals to under root p upon ei into L. So this thing will get. Now solve for p, and you will get p is equals to this, and this is known as p Euler or p critical. Means I can say that this is the minimum load. This is the minimum load above which the column will start buckling. This is the minimum load above which the column will start buckling. Suppose the P load is greater than P critical. Okay. Suppose the P applied is greater than P critical. Then the column will become unstable. Column will become unstable. Remember this. Means it has already started buckling. Unstable means buckled, already started buckling. If P applied equal to P critical means P Euler. Okay? Yes, then it is in the neutral condition. And you can say it is on the verge of buckling. About to buckle. Neutral condition means about to buckle, on the verge of buckling. And third case, if P applied is less than P critical or P Euler, then it is stable and the column is safe. Okay, it is stable and the column is safe. So these are some of the conditions we must memorize. I hope you got my point. Okay, so this is a very important thing. Now the I, the very important part. What about this I? This I is nothing but the minimum area moment of inertia. Remember that. Okay, minimum area moment of inertia. See, what is this minimum area moment of inertia? Suppose the cross section of the column is rectangular. Let me explain. Let's say the cross section of this column is rectangular. Okay, let's say this is B, this is H. So it will have two axes. One is XX, another one is Y. Let's say B is less than H. H is greater. Okay. So what is IXX? That is area moment of inertia about XX axis. It is nothing but 1 by 12 B H cube. Then what about IYY? It is nothing but 1 by 12 H B cube. Right. So we have two area moment of inertia, IXX and IYY. Out of which one is greater? Obviously IXX is greater than IYY. So which is the minimum? I minimum is IYY. Okay, IYY is the minimum among the two. So you can say that the column will start buckling if the P applied exceeds P critical, then column will starts buckling and it will buckle about YY axis. I hope you got my point. So yes, I have explained all these things. Now this is the second what can I say, this is the second thing. One end is fixed and the other end is free. See, this is the fixed one, this is the free. So again, if I apply load P, that is axially compressive load, then it will buckle something like this. You can see here, it will buckle something like this. Okay, so once you apply that same concept which I told you before in the both side hinged part, same concept will be applied here. First find out bending moment and then write the differential equation of it, find the solution, put the boundary conditions. You will get P Euler as this. P Euler, you can say P critical. P Euler means P critical. Sometimes in many of the books, they also call it as crippling load, Euler crippling load also. So it is nothing but pi square EI divided by 4L square, where L is the length of the beam. Now, one thing you can see here, pi square EI divided by 2L whole square. This is P Euler. Okay, so I can write pi square EI divided by L effective square. So what is the value of L effective here? The effective length, which is nothing but 2L. Okay, 2L is the effective length. What was the effective length here? In this, effective length is equals to L. So we will try to write with a common sign, because we will have a common formula for P critical, that is pi square EI by L effective square, and we will get the values of L effective for different conditions. Right? Exactly. Now both end fixed. If both end are fixed, here also fixed, here also fixed, both end are fixed, then again same concept you will apply. You will get this P Euler is equals to 4 pi square EI divided by L square. So if I write P Euler is equals to pi square EI divided by L by 2 whole square, I can write this one like this. So what is the value of P Euler? Pi square EI divided by L effective square. So L effective is L by 2. So the value of L effective is L by 2, which is nothing but the crippling load or P Euler load. So this is the effective length. Okay, L effective, that is L by 2. And then one end is pin, another end is fixed. This is pin, this is fixed. Okay, so here you will see that P Euler is equals to this, almost is equals to. Actually, we will get this value. Then I approximated this value into 2 pi square. So pi square EI divided by L upon root 2 whole square. I can write like this. So here pi square EI divided by L effective square. So L effective value is L upon root 2. So this is the effective length for one end is pin and another end is fixed. So we got 4 L Euler. So the Euler formula is this one only for each and every condition. Here I can write I minimum. Just you have to memorize this L effective value from all the conditions. L effective. L effective for this condition, this is the fourth. This is the third. L effective here is L by 2. L effective for this condition is 2L, and L effective for this condition, that is both side pin, is L. So that's the thing. I hope you got the point. Actually, L effective is nothing but the distance between the two consecutive points where the bending moment is 0. See, at point B the bending moment is 0. At point A the bending moment will be 0, obviously. So for this case we got L effective as L. So I can write, if L effective is equals to L, that means, see, what did I said? The distance between, L effective means the distance between the two consecutive points where bending moment is 0. So this is the two consecutive points A and B where bending moment is 0. Now again, in this case, here we have a point where bending moment is 0. There is no other point where bending moment is 0. So we have a imaginary point which is outside the, so we have an imaginary point. That's why L effective is coming as 2L. We have an imaginary point which is outside the beam, outside the column, where bending moment will be 0, because only here the bending moment is 0 and nowhere the bending moment will be 0. Okay, now in this case both end fixed, the L effective is L by 2. So obviously this is the fixed point, this is the fixed point. The at fixed point the bending moment cannot be 0. So there will be a point which is near to the fixed point, which is near to the fixed point. The bending moment will be 0, which is near to the fixed point. The bending moment will be 0. So the distance between the two consecutive points where bending moment is 0 will be L by 2 for this case. And similarly, L upon root 2 will be for this case for the same reason. Now, I am going to compare the buckling and yielding. Obviously, buckling analysis, this is the analysis, is independent of materials yield strength. You can see we derived P critical is equals to pi square EI divided by L effective square. This is the common formula to all the cases. So you can see here P critical depends upon the material property. This is the material property. This and this is the geometry. E is the material property. I and L effective is the material geometry, means geometry of the column. So this is the buckling analysis result. So it is independent of the yield strength, because nowhere you found yield strength. In fact, yielding consideration should never be totally ignored, but sometimes we should not ignore the yielding. How? See, suppose if I calculate P critical upon area, which is nothing but the sigma x. Sigma x is P critical divided by area. This is the axial stress. This is the axial stress. Suppose this is the column, and in this column, suppose P critical has been applied. So if P critical has been applied, so it is going to buckle, about to buckle case. So some axial stress will be present here. But at the same time, bending will also be there. Or suppose it has just started buckling. So some amount of little bit bending stress will also be there, that has to be taken into account. So I will find out total normal stress, which is nothing but bending stress plus axial stress. If bending stress is present little bit, then we will find out this total normal stress, and we will compare this total normal stress with the yield stress, and that total normal stress must be less than yield stress. Yes. And remember, this Euler equation, this is the Euler equation for P critical, is only applicable for long columns. Yes, I hope you got the points.